Oh, okay, so it works. Okay, so let us start our seminar. So it's my really great pleasure to introduce Professor Domenico Marinucci. Domenico is a full professor in probability and mathematical statistics in Rome, University Tor Vergata. Domenico is, of course, well-known probabilist. I just seen from his webpage, he is top in the list of top mathematical scientists in Italy, but I believe also in the world as well. Marinucci made a lot of substantial contributions to probability theory and statistics, but I believe the most fundamental and well-known about his research about spherical random fields. Virtually, he initiated a lot of directions in this type of stochastic models, and his monograph on random fields in the sphere, probably now classical monograph and reference tool for many statisticians and probabilists working in this area. I wouldn't like to list all prizes and acknowledgements for Domenico, but probably just mention two of them. So he was editor-in-chief of the Electronic Journal of Statistics, leading journal in our area, and recently he was invited speaker for European Congress in Mathematics. Domenico, of course, doing a lot of very interesting research in mathematics and probability of random fields, but at the same time, this area is very closely related to some cosmological research, especially cosmic microwave background radiation, and he was on the tip of European Space Agency, which published several very influential papers, probably each of them with citations of several thousands or something like that. So he is showing how to apply these methods, or how at least these models can be applied to very fundamental things in cosmology as well. So Domenico, you are very welcome.
So thank you very much for such a warm presentation. Many thanks, really. That's it's a pleasure for me to give this talk. It is definitely the earliest talk I gave in my life, because here in Rome it's 8 a.m. in the morning, but still, you know, I wake up very early in the morning, so it's very good for me to have this occasion. Okay, so as it was said 1 minute ago, I mean, my research on spherical random fields has been motivated a lot by applications, and in particular by cosmological applications. And so actually what I'm going to talk about today is also something which is at the interface between probability and motivations from cosmology. And indeed, it has been developed together with other people, which I would like to mention. In particular, Antonio Lerario, Maurizio Rossi, and Michele Stecconi. These three people are mathematicians, but they also have different backgrounds, because Maurizio Rossi is my former student. She's in probability, but Lerario and Stecconi, they work in random fields, but they come from differential geometry. Okay? Whereas Caron and Carron, they were both my PhD students in physics, in cosmology, and when they took care of the applications of what we did and what I'm going to discuss right now. And then other people are working in this area. Okay, more broadly, okay, spin random fields I will mention later on. There are also other important mathematicians that are currently working on this sort of topics. Okay, let me just skip a couple of slides and go directly to explain some motivations, which were exactly those mentioned 5 minutes ago in the presentation. Okay, so this that you see are real data that many of you are well aware of. This is a Planck map on cosmic microwave background radiation. So what is cosmic microwave background radiation? There is now a standard cosmological model which predicts that the universe started around 13 billion years ago in a very hot and dense state where matter was completely ionized. So of course, there was nothing of what we see today, but there was just a fluid which was made up of protons, photons, and electrons. And the mean kinetic energy of the electrons was so high that there were no stable hydrogen atoms. Okay, it's like the velocity of the electrons was too big for them to be captured by protons to form atoms. Okay, so for reasons that have to do with fundamental physics, this means that electrons were free, and the probability that they had to interact with photons was very, very high. So the mean free path of the photons, the particle of light, was very short. In other words, the universe was dark, was opaque, was not transparent to light. Okay, then the universe expanded very quickly. As it expanded, the temperature went down. Okay, and then the kinetic energy of the electrons was no longer enough to balance the electromagnetic potentials of the protons. So the electrons were captured by the protons to form stable hydrogen atoms. So the key prediction of the Big Bang model is the fact that we should live embedded in a flow of photons coming directly from this age of recombinations when the electrons were captured by the protons. Okay, because when the electrons were captured by the protons, the universe became transparent. The photons were no longer interacting with the electrons. So these photons started to travel freely, and to the first order, they travel freely until they reach us. Okay. So this is basically cosmic microwave background radiation. Its existence was predicted already in the 40s. It was discovered only in the 60s, 1960s, by Penzias and Winson. But it was only in the last 10 to 15 years when it was possible to send satellite mission by NASA and ESA to the sky in order to observe not only this radiation, but also the tiny fluctuations of this radiation around its expected value. And these are exactly the data that you see here. So this radiation has an average value which is in the order of 2.73 degrees above the absolute zero. But then there are this average value you can subtract, and then you're left with some fluctuations which are in the order of 10 minus 4, 10 minus 5 with respect to these average values. And the fluctuations are those that you see in this map. Okay, so the red areas are those where this radiation was hotter, and the blue area are those. You can see my pointer, fine? I mean the hand with which I'm pointing somewhere. Can you see it?
Yes, yes, we can see.
Okay, so this is like a map on the sphere, because you can imagine that we are in the center of, like, pretend that the satellite is the center of a sphere, which is just the celestial sky, okay? And then it observes in all directions, it gets this radiation, it measures its temperature, and it gets a map, okay, which to first order is a Gaussian isotropic map with a zero mean, okay, with some regions which are hotter, which are these red regions, and with some regions which are colder, which are these blue regions, okay? And of course, on this, you can do a lot of nice mathematics and statistics, and it opens a way of an enormous amount of very interesting questions in physics, but also in probability and stochastics, okay? So what are the first questions that you can ask? Well, the one very important question to ask is, what is the geometry of these fields, okay? So for instance, you have some cosmological model. This cosmological model can make some predictions on the geometry of these fields, and then you can compare what you observe with the predictions to validate the theoretical model. Now, what do we mean by the geometry of a random field? Now, the first thing to introduce is the notion of an excursion set. An excursion set is something very simple. So in general, you can have a manifold M. In our case, M is going to be the sphere. And then you can have a random field F, okay? Then you fix some threshold, U. U is just a value, can be 0, 1, 2, okay? And then you look at the subset of the manifold, so in our case, the subset of the sphere, where the field is above the level U. So for instance, if you take U equal to 0, you look at the subset of the sphere where the field is positive, okay? This is an excursion set, okay? And you want to characterize what is the geometry of these subsets, of these excursion sets, okay? So in practice, let's go again to real data. So these are the CMB maps that I mentioned before. If you look at this top, normalize them so that they are zero mean and variance 1. So these are, as I told you, first order Gaussian maps. So these are the values where the field is larger than -3. Now, you know that if you have a standard Gaussian, it's basically always larger than -3. So here in this map here, on top on the left, you get just back the original map. Then you raise the threshold level, -2, -1, 0, 1, 2. So you can figure out as like a tide which is raising, okay? It's getting higher and higher, and then it leaves you less space over the water. Okay, so the water is raising, and you see what remains over the water. So, for instance, -2, -1, let's go here to 0. So here you have all these gray regions, which are like the oceans, okay? And then the blue regions are the regions which have remained on top, okay?
Now, as the water gets higher and higher, you get, you know, smaller regions. In the end, they are just small islands which are isolated, okay? And you want to characterize, for instance, what is the area of these regions, what is the boundary length of these regions, how many islands do you have, if there are lakes inside the islands, meaning holes inside the connected regions, and questions like this, okay? So this is the kind of things that you want to address. So how do you do this? Well, first of all, let's go back to some basic results in convex geometry, okay? So let's go to the notion of so-called tube. So pretend that your excursion region is just this square, this blue square that you see, okay? Then around this square, what you can do is you can build what is known as a tube. A tube is just a set of points which are at a distance smaller than some radius rho from the original excursion set, okay? So for instance, you fix some rho and you get this tube. This is like an halo around the original excursion set. Now, there are some classical results in convex geometry that tell you that the measure of this tube, so here we are in two dimensions, the measure is just the area, has a finite Taylor expansion. Okay, so if you want to compute the area of this tube, what do you get? You get a zero-order term, which is just the area of the original tube, this blue region that you see here. Andre, we see everything, okay? The hand and the colors and the fine?
Yeah, we can see it. Yeah, we can see your mouse.
Okay, so there is this blue region, which is a zero-order term, because it doesn't depend on the radius of the tube, okay? Then there is like a linear region, which is this orange thing here, that depends just on the boundary of the original square times the radius, and you get this orange region, fine? Then if you take together these four corners, what you get is a disk, and the area of the disk is pi, which is a constant, times a quadratic term, rho square, okay? So the area is expanded in three terms, constant, linear, and quadratic, okay? Now this is a general fact, because under minimal regularity condition, okay, there is this Steiner tube formula that tells you that the measure of the tube of radius rho around the original excursion set, so to speak, around the original set, has this finite order Taylor expansion, which has a number of terms which is equal to the dimension of the space plus 1. So if you're in dimension 2, it's 3 terms, okay? And then the expansion takes the form powers of the radius, okay, times this omega j are just universal constants. They are like volumes of unit bolts, so they're like pi squares, this divided some gamma functions. But you don't care about what is the exact expression. Just think to this omega j as a universal constant. And then there are these quantities here, okay? This written as Ln minus j of m. And these are the so-called Lipschitz-Killing curvatures, okay? So the coefficients of the expansion, which in dimension 3 are, for the reasons I told you before, what? The area, this was the zero-order term, the boundary length, actually it's half the boundary length for some normalization issue, and then the so-called Euler-Poincaré characteristic, okay, which is the number of connected regions minus the number of holes, okay? Then it can be proved that if you have not only this measure of the tube, but basically any geometric functional which satisfies some rather broad regularity conditions that I'm not discussing here, okay, then these three functionals are still a basis for this more general class. So in short, this is telling you that these three so-called Lipschitz-Killing curvatures, so these coefficients in this expansion, are going to tell you basically everything you want to know about the geometry of your sets, okay? So our goal is what? We want to study what is going, how do these Lipschitz-Killing curvatures, so how do these functionals are going to behave in random circumstances, okay? Now, so the point is, if you have a random field, the excursion sets are random sets clearly, and so these functionals are going to have to be random quantities, okay? So the first thing that you want to study is their expected value, okay? And this is something which has been solved very brilliantly about 15 years ago, a little more than 15 years ago, by Adler and Taylor, okay? So let me introduce some notation, okay? Let's introduce these square brackets here give you what are known as the flag coefficients. What are flag coefficients? Well, they are just universal coefficients that you obtain by taking like the standard binomial coefficient, like Newton binomial coefficients, and then again some constants which are related to volumes of spheres. So these are pi's and gamma functions, but you don't need to know the exact formula. You just need to know that these are universal coefficients, okay? So that's one notation that we need to introduce. Then let's take this rho k of u, okay? Rho k of u, what are they? These are deterministic function, okay, which you obtain by taking derivatives of the Gaussian distribution function. So in particular, they're equal to Hermite polynomials times the Gaussian density. The Gaussian density is this small phi here is just the standard Gaussian density, okay? And then the Hermite polynomials, they come from derivatives of this Gaussian density or distribution, and there is this family of orthonormal polynomials with respect to the Gaussian measure. I mean, the first one is 1, u squared minus 1, u cubed minus, so on, okay? So let's go back. So let's look at this expression by Adler and Taylor, which in my view is really beautiful, which is the so-called Gaussian kinematic formula. So what do you have on your left? On your left, you want to compute the expected value of the Lipschitz-Killing curvature, so this geometric functions I told you before in any dimension. So this is very general, okay? For what? A general random field F. Now let's consider the Gaussian case, but this covers also non-Gaussian circumstances. So this is a random field, Gaussian random field. M is a manifold, could be the sphere, but could be many other manifolds. U, as I told you before, is a threshold, okay? So you want to understand the expected value of this thing. For instance, the expected value of the Euler Poincare characteristic, the expected value of the boundary length of the excursion set, and so on. So this is a linear combination on the right of what? Of these flag coefficients. Flag coefficients are what I told you before. But the important take-home message is that these are universal. They don't care about the manifold. They don't care about the field. They don't care about the threshold. Just some factorials and some pi's and so on. Then there is this function rho k of u. Now this doesn't care about the manifold, doesn't care about the field. It's just a function of u. Hermite polynomials times Gaussian density. And then these are the Lipschitz-Killing curvature, but not evaluated on discursion sets, which in general they are very complicated sets, as you saw before in the pictures, but evaluated on the original manifold. Okay, so meaning, for instance, in our case, evaluated on the original sphere, where they are very simple to compute. Because, for instance, in dimension 2, I told you the Lipschitz-Killing curvature are the sphere, the area. So if you have a unit sphere, the area is 4 pi. Okay, then the boundary length, but the sphere has no boundary, so the boundary length is 0. And then the Euler Poincare characteristic, and this is known to be 2. So that's very easy. Okay. Now, at this stage, you're going to tell me, but this is impossible. What is the trick that can't be? Because not only here what happened on the right is that the role of the threshold and the role of the manifold is completely separated. Okay, it's decoupled, so to speak. Okay, but moreover, where is the field? Because this depends just on the manifold, this depends just on the threshold. Where is the field? Where the field is in this upper superscript here, and it enters in a very nice and very elegant way, because what happens is the following, is that these Lipschitz-Killing curvatures, they are volumes eventually, okay? So they depend on the metric. So the role of the field is to change the metric, okay? How? So what happens is the following, is that you have some random field, okay? Then for this random field, you can evaluate the gradient, okay? So just the column vector of the partial derivatives. This is a random vector, clearly. So because it is a random vector, it has a variance-covariance matrix, okay? This variance-covariance matrix is positive definite, and therefore it induces a new metric. So what you have to do is to compute this Lipschitz-Killing curvature under the new metric induced by this matrix here, which is the covariance of the random gradient. Okay, so this may sound complicated, and in some cases it is. It is also very elegant, but in some cases it's very simple. Because, for instance, if you have a random field which is isotropic, the only thing that you have to do is this thing which is written in the last line, and it is the following. you take the random field, you compute the derivative of the covariance of the field at the origin. So you have a Gaussian random field, it has some covariance function. You compute the derivative of this covariance function at the origin. You get a number like 5. You take the square root of this number, what you see here, and then the new metric is simply the old metric, but rescaled, multiplying by the square root of the derivative of the covariance function at the origin. So for instance, rather than being on a sphere of radius 1, you are on a sphere of radius square root of 5. But the area is very simple to compute. For a sphere of radius square root of 5, the boundary length is T0, the Poincare characteristic is a topological invariant, so it doesn't change. So this means that you can compute these things very, very easily, okay? At least in the isotropic case. I told you before that this covers also non-Gaussian circumstances. For instance, if you take a chi-square field, the formula is exactly the same. The only thing that changes is that this deterministic function rho ku, okay, that in the Gaussian case was the one that I was telling you, Hermite polynomials times Gaussian density. In the chi-square case, that is as this other expansion, which may sound more or less complicated, but it's fully explicitly known. So it's like an exponential times some polynomials times some constants, okay? But the important thing is that it's fully deterministic, fully explicit, okay? Okay, so this formula is very nice and very important, and it has been applied a lot, for instance, on CMB data, just to, for instance, I've seen before that there is Professor Ian Sloan in the audience, that he has also worked a lot on needlets. One thing that has been done a lot on, which I'm not discussing in this talk, needlets just a form of filtering of spherical wavelets, okay? So what has been done a lot on Planck papers is to compute the excursion set for needlet fields, okay? And to compute their actual value on the data with the expected values which were given by this formula, okay? And to see how much they would fit, okay? And another thing which, okay, in principle it could be done on CMB data, although here I'm cheating a bit because there are, some practical circumstances why exactly this thing that I mentioned in a second is difficult to do. But the point is the following, is that when you have a random field on the sphere, the random field you can decompose as a number of components of random eigenfunctions living at different frequencies, this FL, okay? So these are random eigenfunctions, which are themselves a sequence of random fields with some expected value, some covariance, which is given by this PL of XY, which is also called Legendre polynomials. You want to apply to these fields the Gaussian kinematic formula. Well, this is very simple to do. The only thing that you need to do is to compute the derivative of the covariance at the origin. The derivative of the covariance at the origin turns out to be just the corresponding eigenvalue, this LL plus 1, these are integer numbers divided by 2. Then you have this expression of the derivative of the covariance at the origin. And then you just need to replace this expression for the derivative of the covariance at the origin inside the linear combination I told you before, and you get these very explicit forms for the expected value of the Poincare characteristic, expected value of the boundary length, expected value of the excursion. Okay, and this is something on which there's been a lot of work where I've been involved. I mean, this Cammarota, Rossi, Todino, Vidotto are all my former PhD students. Giovanni Beccati, I think you know well, and Igor Wigman also is in King's College. I mean, we work together a lot on these issues. Okay, now, so this in some sense was just a background. Okay, so these are all things that have been done in the last 10, 15 years. Okay, now what's next? What is going to come in terms of motivations from cosmology in the next 10 years or so? Okay, so what's coming next is so-called polarization of the cosmic microwave background radiation. So this is going to be the object of many experiments. Most important one is LightBird, for instance, which is a joint collaboration between the Japanese Space Agency and European Space Agency, but there are also many ground-based observatories that work on this, and many other experiments that I'm not going to discuss. So what's the point? Okay, so I tried to explain quickly before what is CMB, okay, cosmic microwave background. It's this random field on the sphere, scalar random field. So in every direction on the sphere, what you observe is some temperature, which is basically the temperature associated to the photons that are coming in this certain direction. Okay. Now, the very important thing, again, this thing that you see here are again real data from. Okay? So the very important issue is that these photons, while they travel towards us, coming from this last scattering surface, not so this moment when the electrons were captured by the protons and the photons started to move freely. Now, just out of Maxwell equations, basic electromagnetic theory, basically what these photons do is that while they travel towards us, they sort of like draw some ellipses in the plane which is orthogonal to the direction where they move. Okay, so from cosmology, the next frontier of cosmology is the fact that they will observe random fields that they don't have scalar value. Scalar value means I give you a direction, I give you a point on the sphere, you give me a number. I ask you what is the temperature in Australia, in Adelaide, or in Melbourne, or in Victoria. Right now, you give me one number, 20 degrees, 30 degrees, 40 degrees. So that's a scalar random field. Now, this is something more sophisticated in a sense, because in every point on the sphere, you have a tangent plane at that point. And on this tangent plane, you observe an algebraic curve. For instance, in this case, just some lines with undirected vectors. Okay? Okay. So this is what? Mathematically, it's just a random section of a fiber bundle. Okay? So you have the sphere, which is the base of the fiber bundle. In every point on the sphere, you have the tangent plane. And then on the tangent plane at this point, you have some, for instance, a line or an ellipse or another algebraic curve. Okay? So this is a random section of a fiber bundle. Okay? And this is exactly the kind of data that the physicists are observing now. Okay? So you want to address similar questions as the one I mentioned before, and other questions that have been addressed, including, for instance, construction of needlets or wavelets in this field, if somebody works in this area. Okay? But in this more general circumstances. Okay? So what we have is really, I mean, I don't know if this picture is clear enough. You can imagine a photon is traveling like in this direction, bottom to top. But while it travels, okay, it draws these ellipses. Okay. So that's a polarization, different form of polarizations. Okay. Which again they are very important for physicists for a number of reasons. Okay. So how do somebody wanted to ask something? No. Okay. So what is the key point? The key difference is that if you have a scalar random field, once you decide the location on the sphere, then the value of the field is decided. Okay. If I tell you the name of the city, Melbourne, then you can tell me the temperature and that's it. But if you have like these more geometric structures, then it's not enough to know where you are looking at, but you have to also to fix some coordinates in the tangent plane. Because if you rotate the tangent plane, the value of this field is going to change. Okay, that's the big issue. Okay, so in particular, so if you think of this like ellipses that are drawn on the tangent planes that comes towards us, then to these ellipses you can associate a quadratic form, a 2x2 matrix, okay, which is in fact what is computed by the physicist. And in particular, this quadratic form is usually decomposed in terms of so-called Stokes parameters. So in other words, you can imagine that at every point on the sphere, what you observe is a random 2x2 matrix, okay, which depends on the choice of coordinates for the tangent plane at that point, okay? So this 2x2 matrix, you can express into three parameters. This parameter I, okay, is like proportional to the trace of the matrix. So you know that the trace is invariant to rotation. So it's a scalar quantity, which doesn't depend on the choice of the local coordinates. And it corresponds to the scalar fields we were considering before. So this ellipse has a scalar component, which is this I, this intensity, which is like the temperature that we were mentioning before. But then there are also these other parameter Q and U, which, if you remember some Maxwell equations and electromagnetic theory, these are what are known as the Stokes parameters, okay? Q and U, okay? And this Q and U you can do as what? Okay, you have this tangent plane. You can identify it with the complex plane, okay? And then Q can be like the real part of this complex plane, and U the imaginary part. But, you know, again, it's important that these are not really simply a complex valued random field, because they are not invariant to the local choice of coordinates. And in particular, they change with this spin rule. So what is a spin field? What the title I had, geometry and topology of spin random field. So what is a spin random field? For instance, in this case, spin 2 random field. A spin random field is an object, complex valued in general, such that if you rotate locally the tangent plane by an angle gamma, then the value, the complex value of the field is rotated by this factor exponential of minus I2 gamma, okay? So spin 2 means that here you have a 2. If it was spin 3, it would be 3 gamma. Spin 10, e exponential of minus I10 gamma, okay? So for instance, an ellipse is a spin 2 object. Why? Because if you rotate by 180 degrees, you get the same ellipse. And in fact, here you get 2 pi, a rotation by 360 degrees, and this would be exactly 1, okay? And nothing would change, okay? So a vector, for instance, is a spin 1 object, okay? Because you need to rotate by 2 pi to get the same vector. An ellipse, you need to rotate just by 2 pi divided by 2. If you have like, I don't know, a quadriflower or something like that, like if you have the symbol of Mercedes, the car, then this would be a spin 3 object, okay? And in general, okay, this you can think of spin S objects, where in each point of the sphere you have this symmetry of order S. Okay, is this clear? I hope. Okay, so again, these are real data. So what you see here is that you can think that in every point here you can take the tangent curve to these level curves, and the tangent with no direction gives you the orientation of the spin in that point. Okay, so what we want to do is to study these fields, which clearly is much trickier than what we discussed before. Okay, so why is it trickier? Because even if you try, for instance, let's assume that we want to do the geometry of excursion sets. But what is an excursion set here? This is hard to say. First of all, because these fields are complex valued, but much more importantly, because they are not intrinsic. The value is not given by, once you give you the point, you don't know the value of the field. Not only not even the complex value, because the value is going to depend on the choice, the local choice of coordinates. Okay. So how can we study these things? Well, okay, a bit of geometry to understand what we can do. The first thing is the following. I mean, if you have a rotation in SO3, okay, it's a well-known fact that you can always parameterize these rotations by 3 angles, which are known as the Euler angles. Okay, so what does it mean? So any rotation on the sphere you can do like the following. Okay, so assume that you want a rotation that brings you from Rome to Melbourne, okay, or to Canberra, to Adelaide, or whatever. Okay, so what you can do is the following. Assume that we have here in Rome an axis which goes from the center of the Earth and comes out here in Rome. Okay, so the rotation you can always imagine as first I go down till I go to the latitude of Melbourne. Okay, then I rotate till I get in Melbourne. So there are 2 angles, one to go down to get the right latitude, and another to go along the parallels to get to Melbourne. Once I am in Melbourne, there is one more rotation I can do, because I can decide the orientation of the coordinates in Melbourne. Okay, the orientation of the tangent plane in Melbourne. Okay, so it's like if I have a book here in Rome with some direction, okay, and I want to rotate it and bring it in Rome, I have 2 angles to bring it in Melbourne, 2 angles to bring it in Melbourne. Just go down and then rotate it in Melbourne. Then once I am in Melbourne, I can do one more rotation to decide what is the orientation of the book in Melbourne. Okay, so that's the 3 Euler angles. Okay, now so the group of rotation SO3 is parameterized by these 3 Euler angles. Now with the same parameterization, I can make the spin random field a scalar valued, no longer fiber bundle, but a scalar valued random field, but not defined on the sphere, but defined on the group of rotations. Why? Because the first two angles are going to tell me what point in the sphere I'm looking at. Okay, so like starting from the North Pole, with the first two angles, I arrive in some direction on the sphere, and I decide in what direction I'm looking. Okay, and then with the third angle, I decide what is the local choice of coordinates. Okay, so in this way, I can actually identify one point on the sphere and the orientation of the tangent plane at that. Okay, so the idea is, one thing that I can do to study this random field is to lift them from fields to the sphere, which are not scalar valued, to random fields on the group of rotation SO3. Okay, so I study random field on this group of rotations SO3. Okay, now how can I study random fields on the group of rotation SO3? Now something more from group representation theory. Okay, so the point is the following: if I have a group, I can define a matrix representation simply associating the elements of the group to matrices. Okay, so to one element, I associate the matrix M of G1. To element G2, I associate the matrix M of G2. But I do this association in such a way that the group structure is maintained. So to the element G1 times G2, I associate the product of the matrix MG1 and MG2. So this is the representation. Okay. So the representations of the group SO3 are known, and then there is a very important theorem from group representation theories that it tells you that if you look at the space of square integrable functions defined on the group, okay, then you can do some sort of Fourier analysis, to harmonic analysis, and express these functions in terms of the direct sum of what? Of the elements of the matrices I quoted before. Okay, so you have a family of matrices, okay, and the elements in this family of matrices give you an orthonormal basis for the L2 space of these functions on the group. Okay. Now this group representation of this function of the group is well known. Okay, and it's given by these so-called Wigner matrices. Okay, so these are matrices of dimension 12 plus 1 times 12 plus 1. Okay, where L are integers. So you can think of them as 12 plus 1 columns. Okay, each of these columns has 12 plus 1 elements, and each of these columns spans a different space. So index these columns, fix L, which is an integer, okay, like 10. So you have a matrix which has dimension 21 times 21. So it means that it has 21 columns. No. Okay, so you look at each of these columns, okay, and you look at what is the space that is spanned by these columns, okay. So each of these columns span a space of functions of order of spin S. So if you order like them -10, -9, -8 until 10. So if you look at the central column, okay, these are functions of spin 0. What are the functions of spin 0? The functions of spin 0, by definition I told you before, are the functions that do not depend on the local choice of the coordinates for the tangent plane. Okay, so these are exactly the scalar functions. So if you look at the central column, okay, you get this set of functions, which are the well-known spherical harmonics for those of you that have worked a bit on the sphere, and these are just a basis for the space of functions, scalar functions on the sphere. So these are just the elements to do standard Fourier analysis on the sphere. But if you look at the other columns, then you have the functions that are spin 1, spin 2, spin 3, and so on. So these are bases for spin 1 functions, spin 2 functions, spin 3 functions. Okay, so you can do sort of Fourier analysis on these more general spin functions on the group. Okay, so the central column, as I told you, was this function of spherical harmonics. And in general, you have spin S. Spherical harmonics are eigenfunctions of the Laplacian on the sphere. The different spin S are eigenfunctions of a more general Laplacian operator which is spin S. So the key take-home message is what? This way, what we can do is we can raise the random field to be a random field on the group, okay? And it is now a scalar valued random field on the group, okay? Now, this scalar valued random field on the group is complex, takes values as complex numbers, but one can prove that the real and imaginary parts are actually one, the translate of the other, okay? So it's enough to focus, so they take the same values in different points of the sphere, okay? So if you focus just, for instance, on the real part, you are not going to lose any information. So the bottom line is what we try to do is the following. With this trick, from a field which is, so takes value in a spin fiber bundle, it's random sections, we lift it up to a random field, which is no longer on the sphere, but it's on the group SO3, but on this group SO3, it is now scalar valued, okay? And so because it is scalar valued, what we can do, let me skip a bit of these things, we can do the same thing as before. So we can go back to use Adler and Taylor results, okay? And we can compute the Lipschitz-Killing curvatures, the expected value for the excursion sets, which are now no longer excursion sets on the sphere, but are excursion set on the group, okay? So what we did, so skipping some details, is what we did is we did, you know, a lot of computations based on differential geometry to compute what is the gradient on the group SO3, what is the S on the group SO3, and especially what is the metric induced by the covariance function on the group SO3 in order to be able to apply the Adler and Taylor formula, okay? So these computations are not trivial, but they are doable, okay? And so if you do all these computations, what you get is, so here is, for instance, I mean, if you remember what I was telling you, the key trick is that now you need to compute the new metric, which is induced by the covariance metric of the covariance matrix of the gradient vector, okay? So we computed the gradient vector on the group, we computed its covariance matrix, and then we computed the Lipschitz-Killing curvature with the metric induced by this new the covariance matrix of the gradient, okay? And out of this, we were able to compute the expected value of these Lipschitz-Killing curvatures for the excursion set for all the geometric functions that I mentioned before. So the expressions, you know, are those that you see here. They may be more or less transparent. For this is the expected volume is just given by the tail of the Gaussian distribution function times some normalizing factor. Then there is sort of boundary surface, which is again some deterministic function times some constant time a factor, which just depends on the derivative of the covariance function on the group, and so on and so forth. So we have the explicit expression of all of these things, and then we have also a number of simulations that show actually that these results work. Okay, so these are simulations on CMB polarized maps. Okay, so the continuous lines are the predictions, and the dots are the simulated results with many replications. Now, okay, so the expected values fit, that's mathematics works. One thing that I want to mention, which is perhaps interesting for future work, is the following: is that if you look at these halos, okay, if you look at these halos, they tell you the variance of these geometric functions over different realizations. Okay, so here there is an interesting phenomenon, because you see that at some level, like at level 0, the variance appears to be 0, which means in practice that it is a smaller order than a smaller order of magnitude with respect to the other thresholds. Okay, so this is something that was observed also for scalar random fields. Okay, that actually they turn out to have some cancellation points where the variance is much smaller, and it was recently explained in a number of papers working with Hermite expansions and so on. So apparently the same sort of phenomenon is also happening in this more general framework. Okay, but still remains to be explained. Anyway, in terms of the expected value, as you see, the theory and the realizations, they fit very well. Okay, now I think that I have just a very few minutes left. There was something else that I wanted to say, but I believe I will not have time. I'm just going to mention it very shortly. So, I mean, if you have in mind applications like application to polarization, then what I discussed in some sense is doable and gives you clear-cut predictions, and it's yeah. It has actually also been applied on real data, as I mentioned in some paper, like with my PhD student in physics that I co-supervised, which is called Javier Carrondo. From the purely mathematical point of view, one could ask another question, okay? Which is, so these fields now depend also on a spin parameter S, okay? S is the parameter I was mentioning that tells you the kind of symmetry that these fields have with respect to rotation of the local tangent plane. So one question which is mathematically more interesting, although it's not directly motivated by the physics, is the following. What happens if you consider an asymptotic framework in which you allow also the spin parameter to grow to infinity, okay? Well, as I said, I don't have time to discuss it, okay? But it's just one thing I want to mention. It is the following. Now, if you study this literature on geometry of random fields, okay, there are two sorts of benchmark models. One is called Berry random waves, which is the model that you obtain in the limit when you consider random eigenfunctions of the Laplacian in the scalar case, okay? And you take eigenvalues that get larger and larger, okay? Then this has a limit, and it gives you a model which is called Berry random waves, which has been very much studied by a lot of people. The other model, which is often studied, starting from Smale about 25 years ago, are so-called Costland polynomials, okay? This also has a limit if you consider polynomials of degrees that get larger and larger. And as a limit, it gives you so-called Bargman-Fock random field, which is something very important in quantum field theory. So to do the geometry, the kind of questions I discussed in this talk, there are two sorts of benchmark models, which are Berry random waves and the Bargman-Fock model, okay? The two limiting cases. So what happens when you consider the spin random fields that I discussed today, and you allow also the spin parameter to diverge to infinity? Well, if you fix carefully the asymptotic theory in a way that I don't have time to discuss now, there are two limiting cases. One limiting case is where the spin parameter grows slowly. In this case, you get Berry random wave model. The other case is where the spin parameters grows as quickly as possible. In this case, you get Bargman-Fock model. In between, you get a sort of class of random fields which interpolate between these two benchmark models and gives you continuously all the fields that interpolate between the two, okay? And in the limiting cases, these two well-known special cases. So, I mean, as a concluding remark, what I wanted to tell you is the following, is that these spin random fields, they have strong motivations from cosmology, but mathematically they appear extremely interesting objects, okay? Because they allow you to generate complex versions, so to speak, of the two standard benchmark models which are studied in random geometry, which are Berry random wave and Bargman-Fock. But moreover, they allow you to interpolate continuously between the two according to the choice of the spin parameter, okay? So in some sense, they generalize both benchmark model and they allow you to consider a wider class between the two. I mean, this would require much more time, and so I'm not going deeper into this. Okay, okay, I'll skip all this. Here I have some more simulations and so on, and then a list of ongoing or future topics. Very last sentence I want to say before I close. Okay, I mentioned the people with whom I worked most in this area, but there are other people, of course, for instance, Andriy Olenko knows them well, because in some sense, there's always been a tradition from the school in Kiev working on random fields, even from the 80s and 90s, which goes back to Yadrenko and all the students, and in particular on the spin issues, for instance, Nikolai Leonenko, Lyudmila Sakhno, and Anatoly Malyarenko, they've also worked a lot. So, I mean, I didn't mention, time was short, I didn't mention also the related works in this area, but I wanted to mention that there are also important papers from these people as well. Okay, I think that my time is over, more or less, so maybe I will stop here.
Okay, thank you, Domenico. And especially big sense that you try to explain for people from not this area how it works with all these toy examples between Rome and Melbourne. So
yeah, it's a bit technical as a topic, so I mean, I try to sort of give the you know, the intuitions.
Yeah, so if you have any questions, just please unmute yourself and just ask. Dominica, probably I will ask one. So you just mentioned unit chaos expansion. So if you just fix S, so types of limit, say theorems which you consider, it would be just like for maybe with different asymptotics, but something similar like you consider for scalar random fields. That, for example, some limit theorems for eigenvalues or what kind of maybe specific limit theorems could be here?
No, okay, that's a very good question. In a sense, it's something that we are trying to address. So the point is the following: if, for instance, when you work on random fields on the sphere, the first thing is to understand what kind of limit you want to do. Okay, because the sphere is a compact space, and so it's not probably the most natural thing to do standard large sample theory where you imagine the sphere that is growing larger and larger, okay? Because, for instance, in cosmic microwave background, you have just one sphere, and the radius is always the same in some sense. So the asymptotic which has been most popular is the one, for instance, to do some kind of decomposition, which can be in terms of eigenfunctions or in terms of wavelets or needlets or things like this, and then study the asymptotics as the frequency gets larger and larger. So as you look at smaller and smaller scales, okay? Which can be smaller and smaller scales in terms of the eigenfunctions or smaller and smaller scales in terms of wavelets, okay? Now, the same thing basically you can do here, okay? Because these spin random fields, they also have decomposition in terms of random eigenfunctions with different eigenvalues, which are eigenfunctions of a spin Laplacian operators. And you can even define things as needlets or wavelets. Needlets are kind of spherical wavelets on the sphere, on which also many people in the audience have worked. You can define a form of spin needlets on the sphere, and then study the asymptotics as the scale of these needlets or the scale of the corresponding eigenfunctions gets smaller and smaller, so the frequency gets larger and larger, okay? So this you can do probably using, again, Hermite expansion and so on and so forth, okay? So in a sense, this is related to to this plot I was showing you before, okay? So in the case of scalar random fields, what happens typically is that for these geometric functions, what you can do is you can decompose them into different Hermite polynomials, okay? And then what turns out is usually there is a single component, so a single projection on one Hermite polynomial that dominates all the others, and this makes this asymptotic quite doable, okay? And then what happens in the scalar case is that at some thresholds, for instance, at 0 threshold, this single component disappears and you have a different asymptotics. Now, our conjecture is that something similar is happening for the spin as well. And our conjecture is motivated exactly by these simulations here. Because here you see that, for instance, at 0 level, okay, the variance, these halos are the fluctuations in the simulations, okay? So you see that at 0 level, the fluctuations are an order of magnitude smaller. So it's natural to conjecture that something similar is happening into this spin case, that you can do like an Hermite expansion, like an expansion into causes, okay? And then at some thresholds, a single cause is dominating, and then the single cause is disappearing at some other threshold, for instance, at 0, okay? And this makes the variance smaller. So if this is the case, there are a number of things that are likely to be doable, okay? Because when a single cause dominates, it is well known by many years, by work, you know, by Dobrushin and Mayer and Taku, now more than 40 years old, that we have this reduction principle. When there is a single cause projection that dominates over all the others, it's relatively simple to get central, non-central limit theorem, asymptotic variance, and so on. So because of these simulations, we conjectured that something similar may be happening here as well. And you know, we are sort of thinking about it, but we don't have rigorous results about that yet.
Very good. Any other questions or comments, please? Okay, maybe then I again ask one more, okay, because people shy somehow. Say your usual CMB, you can consider in some sense as a realization of some partial stochastic differential equation, yeah? So it's like, would be like physical mechanism why it's appeared. What kind of maybe similar differential equations, stochastic differential equations can lead to these types of fields?
Well, okay, this is going to be that's an interesting question and an interesting topic for research, because certainly you can think to differential equations as it was done in the CMB. The point is that there must be differential equations whose values, the values they take, they are not actually numbers or scalar, but they are like random tensors or random sections of a fiber bundle. I mean, another way to see these things is like a random field, which in each point gives you a random matrix, okay? So it should be like a stochastic differential equations, which takes value in a space of random matrices in the different points on the sphere. So, I mean, it is certainly something which one can think of, but you know, it's more general than what has been done so far.
Okay, thank you. So if there are no other questions, let us thank Domenico for very interesting talk and for very kind and nice explanations just to people who are not from this area. Okay, so enjoy your evening or morning or day. And I just would like to remind that the next seminar would be just in 2 or 3 weeks. So it's already on the seminar site, but we will add details later. Okay, thank you, Domenico.
Okay, thank you very much.
Thank you again for the invitation.
Okay,
Thank
bye-bye.
you.
Bye.
Bye.